Good day. So in this video, I'm going to show you how to solve for the eigenvalues and the eigenvectors of a 2 by 2 matrix. Basically, we can extend this with a 3 by 3 one, but for the sake of demonstration or for an easier way for you to see or understand how to solve for the eigenvalues of a matrix, we'll start off with the most simplest case, which is a 2 by 2 matrix. Now, eigenvalues are essential in system of linear equations in a sense that eigenvalues or solving for the eigenvalues or eigenvectors of a matrix allows you to simplify or to decompose a really complex matrix into a more simpler and into its more simpler components. Eigenvalues are also essential in knowing the shape of a given multivariable function. So something that, of course, that you can simply do in a single variable functions by just looking at the second derivatives, which we will see later. But for multivariable functions, it is essential for us to know the steps on how to solve for the eigenvalues because it gives us an idea, a picture of what the function basically looks like. This is essential not only in system of linear equations but also in optimization or optimizing multivariable functions, especially if we don't know beforehand the shape of the objective function, right? So going back to your notes, the eigenvalues of a matrix is basically alpha, right? Alpha that satisfies this identity, right? So if we rearrange the terms, we're basically getting a minus alpha identity, right, times x, okay, right, times x and equal to 0. Okay, so alpha is the eigenvalue or eigenvalues, right? Vector, the eigenvalues, and x here is the eigenvectors. Now, eigenvectors are supposed to be non-zero, so this equation, for this homogeneous equation, we have a non-trivial solution. And having a non-trivial solution implies that the determinant of this matrix is 0 or A minus alpha I is singular, right? No, or having that information, we'll be able to solve for the eigenvalues of any given matrix. So how do we do that? So let's start off with the simplest numerical example, A matrix A, right? So let's construct A minus alpha I. So to construct A minus alpha I, okay, we'll just copy this matrix, copy this 2 by 2 matrix. Of course, you can do this with a 3 by 3. You just have to follow the procedures or the steps. Although, of course, if you have a 3 by 3 matrix, it implies that you'll have 3 eigenvalues, right? For a 2 by 2 square matrix, you'll have 2 eigenvalues, and correspondingly, you'll have 2 eigenvectors. Okay? This will be essential in our next chapter on eigendecomposition, which basically allows us to simplify or decompose complex matrix with unknown values, practically unknown values, and decompose them into their um, component vectors and matrices, wherein the vectors would be the eigenvectors and the matrix would be a diagonal matrix containing the matrices eigenvalues. So for a more simpler exercise, let's follow through. This is actually already in the slides, but if you're still confused with the steps, I will show you how to solve for the eigenvalues on a step-by-step basis. So if we have alpha I, so this means that this is matrix A. The first term is the first set of the first matrix here would be matrix A, and this would be alpha, okay, times identity. Right? The identity matrix contains 1 and zeros. Okay, so simplifying this, right, we'll get another 2 by 2 matrix. So this is going to be 1 minus alpha. Okay, this is 0. This is negative 1. Negative 1 minus 0 is negative 1. You have 2 minus 0, so that's still 2, right? And you have 4 minus alpha, right? So basically, this matrix will be your alpha minus AI. So just to demonstrate, so this alpha minus AI, sorry, a minus alpha I, I'm sorry, is equal to this 2 by 2 matrix. Now, to solve for alpha, we will use the fact that this is a singular matrix, and being a singular matrix implies that the determinant of a minus alpha I must be 0. Okay, so if I solve for the determinant of a minus alpha I, it must be 0. And what's the determinant of a minus alpha I? The determinant of a minus alpha I is obtained by, of course, getting the determinant of this 2 by 2 matrix. So you multiply the diagonal terms first. So that's going to be 1 minus alpha times 4 minus alpha. Okay, plus 2. Because you have here 2 times negative 1, negative 2, but you subtract it, so it's going to be positive 2. And set it equal to 0. So if we try to solve this, if we try to evaluate this function, right? If you try to evaluate this expression, you will see the more familiar quadratic form, right? So you have two unknowns, right? Or so you have one unknown basically that is a squared term or a polynomial of order 2. So you'll get something like 4 um, minus 5 alpha. Okay, because 1, negative 1 alpha, negative alpha plus negative alpha minus 4 alpha, that's 5 alpha plus alpha squared plus 2, all right? And simplifying it further, you'll get the usual quadratic equation, right? So alpha squared minus 5 alpha plus 6 equals 0. Okay? Now, if you try to factor this polynomial, you will get the roots of this quadratic equation, which means you'll be able to solve for alpha, right? So factoring this out, you will get alpha minus 2 and alpha minus 3 equals 0. So either of them will be equal to 0, and therefore the solution, i.e. the eigenvalues of this matrix, would be alpha equals 2 and alpha equals 3. So you have two eigenvalues, right? Now, how do we solve for the eigenvectors? Okay, so we do it one by one for each eigenvalue, right? So it's just a matter of substituting those eigenvalues back in the equation, right? Or back in this linear equation, okay? So suppose we start off with alpha. Let's use a new slide. Or start off with alpha equals, okay, we start off with alpha equals 2, then substituting it back in the matrix, okay, we have 4, I'm sorry, you have 1 minus alpha, right? So you have 1 minus alpha, you have what, negative 1, and then you have 2, and you have 4 minus alpha. And then here you have the vector of x1 and x2, right? So the goal here is to solve for the values of x1 and x2, considering the fact that this equation, this system of equations would be equal to, or should be equal to 0. So both of them should be equal to 0. So I'm just going to plug in alpha here. Okay? I'm just going to plug in alpha here, and then let's revert this back in its equation or system of equation form. All right. So that's going to be or well, just to show you what happens, if I plug in 2, I'll get 1 minus 2, that's negative 1. This is still negative 1. This is still 2. And 4 minus 2 is 2. Okay. You have x1. You have x1, you have x2. This is the right-hand side is equal to 0. Okay. Now, reverting it back in its equation form, you will get negative x1 minus x2 equals 0. Okay. And then you have 2x1 plus, 2x1 plus x2 equals 0. Okay. Now, to solve for the eigenvector, we'll have to make some assumptions. So suppose, I have a new slide. So let's copy this equation. So suppose x1 is equal to 1. Right? Let's assume that x1 is equal to 1. Right? Therefore, using the first equation, you'll have negative x1 equals x2, and therefore x2 is equal to negative 1. Right? And if you try to plug this in, back here, back in the second equation, you should still get the same result. So if x1 is equal to 1, right? If x1 is equal to, let me, right? So we should replace this with 2x2, right? So using this result and plugging this back in the second equation, you should still get the same outcome. That's that the left-hand side must be equal to 0. So if I plug in 1 here, you'll get 2. If I plug in negative 1, you'll get negative 2. So 2 minus 2 equals 0. And therefore, the associated eigenvector for the eigenvalue alpha, let's denote that as alpha 1 equals 2, is x, right? Have 1 and negative 1. Okay. Now, how about for alpha? Alpha 3? Right. So for alpha, for alpha equal 3, you do the same steps, right? So let's denote that as alpha 2, denoting it as a second eigenvector. Right. So doing the same steps, okay, you'll end up with this system of equations, right? So you have 1 minus alpha, so that's 1 minus 3, that's negative 2, right? You have negative 1, another negative 1 here. You'll have 2, right? 2, and then 4 minus 3 would be 1. Okay. Then you'll have the vector. You have your eigenvector here. The next bracket. So x1, x2, the right hand side remains to be 0. Right? 0, 0. Now, reverting this back to its equation form, you'll have negative 2x1 minus x2 equals 0. And then you'll have 2x1 minus x2 equals 0. Okay. Now, again, let's make some assumptions, and probably we can use the second equation to do so. So let's suppose that we're given the second equation, 2x1 must be equal to x2. Now, if I assume x1 to be equal to 1, then x2 would be equal to 2, right? And that also makes sense since, well, if you plug this back in here, right? If you plug x1, okay. Oh, sorry, this one is supposed to be plus. I'm sorry. Sorry about that. So that's 2x1 plus x2. And therefore, you'll have negative 2x1. So uh, suppose you have x1 equal to 1, then x2 must be equal to negative 2. Okay? And that also, again, makes sense because if I plug in 1 here, right, this becomes negative 2. Plug x2 here, you got positive 2, and it will still be equal to 0. And therefore, to sum everything up, for alpha 1, right, for alpha 1, which is equal to 2, right, the eigenvector x is equal to 1 and negative 1. Okay? And for alpha 2, which is equal to 3, the eigenvector will be equal to 1 and negative 2. Okay. Now, this will have a very useful applications later on, particularly in matrix decomposition. Okay. But as it is, for a 2 by 2 matrix, or probably for a system of linear equations with two equations and two unknowns, this eigenvalues will be very informative later on. Okay. Now, you may ask, do you really have to make substitutions? Well, that's the only thing that you can do, no? Because basically, your coefficient matrix is singular, and the only way for you to make sense of what x1 and x2 is by substituting certain values. Okay. So that's for the numerical example. Now, what if we encounter something like this? No? Suppose we have f equal to some matrix of parameters. If you notice, I derived this directly from the slides. All right, so this is practically an example in time series econometrics. All right, this will be very useful. Right? This is a way for us to, well, simplify higher. This is a way for us to simplify expressions with higher ordered lags into into an expression, into a linear expression that has only one lag. Okay, that simplifies. That's a simplification basically. Okay. So basically, what we did is we simplified an autoregressive process of order 2 or a series with two lags into a first order matrix form. Okay. So this will come in handy, or solving for the eigenvalues later on will come in handy if you wanted to solve for the effect, basically the effect of the first lag of the series, right? And probably you'll encounter this in your time series econometrics later, right? So how do you solve for the eigenvalues of matrix F, right? So let's denote that eigenvalue as lambda, right? So the matrix will look like this, so lambda I, right? And the determinant of this matrix must be equal to 0. Okay. Now, what is f minus lambda I? So f minus lambda I is basically equal to phi p1 minus lambda, right? You have phi 2, you have 1, and you have 0. And the determinant must be equal to 0. So what would be the determinant of this? Oh, sorry, you still have lambda here. Right? You have lambda because it's supposed to be in the diagonal. So what's the determinant of this? Or sorry, what's the value of lambda that will satisfy this singularity condition? Well, you just copy this. Right? So we'll just take the determinant of this matrix. So that will be equal to phi1 minus lambda times lambda minus phi2. That's equal to 0. Now expanding it, you'll get another quadratic form, right? And this is the thing about modeling, right? Particularly with the higher ordered lags, right? Higher ordered autoregressive models. It's more practical to convert them into a first order matrix form, right? Because it's easier to manipulate. Right? It's going to be easier to manipulate, and it will just take a couple of matrix operations in order to get some practical, or just in order to get some analytical, in order to get some analysis out of the model, right? If that even makes sense, right? So let's expand this. So you'll have phi1 lambda. Okay, you have phi1 lambda minus lambda squared minus phi 2, and that's equal to 0, right? And well, um, multiplying the negative terms out, right? Multiplying the negative terms out, you'll have lambda squared minus phi1 lambda plus phi2, and that's equal to 0. Of course, you cannot factor this out anymore because, well, you have a lot of unknowns. So if you have a quadratic expression and you wanted to find the zeros, i.e. the lambdas, the values of lambda in this scenario, right, you can use the quadratic formula. Right? So the quadratic formula, if you still remember this, and I do hope that you still remember this, because it will come in useful for quadratic equations that don't have that cannot be factored out, right? And this is typical in solving eigenvalues, right? So the formula would be, this is a, the coefficient of lambda squared is a, this is b, and this is c, right? So you'll have positive phi1, right? Because this is already negative, but in the formula, recall, right? Let me just put it here. The formula for the quadratic formula should look like this. Oops. Right. So x is equal to negative b plus or minus square root b squared minus 4ac over 2a. All right. So since phi is already negative, right, multiply it with another negative number, you'll get phi1, right, plus minus, and you have another square root here. You have phi squared, right, phi1 squared minus 4 times 1 times phi squared, phi2 squared, right, phi2 squared over 2, right, because a is equal to 1. So you have two values here. So therefore, the eigenvalues will just be equal to phi1, phi1 equals, well, practically this. Oops. But this becomes positive. The first, the first eigenvalue, sorry, the first eigenvalue would be this, and the second eigenvalue would be the negative. The negative of the would be the negative of the square root. Okay, so this will be the corresponding. Will be the corresponding eigenvalues. So in the next video, we're gonna have more of these eigenvalues when we try to do matrix decomposition. Right? This is again useful in time series econometrics and probably in some other applications as well, which requires you to obtain a decomposed version of more complex matrices. Okay. So see you in the next video.